Welcome to Tech Mastery Guru. In this video, we will explore the AI Agent Playbook, from prompting to production. This comprehensive video cuts through the hype, delivering practical and foundational knowledge for building powerful AI agents and intelligent systems. This course moves beyond buzzwords, offering a deep dive into building AI agents. We'll cover fundamentals, advanced topics like model context protocol and multimodal capabilities, and deployment strategies, transforming LLMs into production-ready systems. At their core, agents are an abstraction layer over LLMs. They act like AI employees, maintaining context, fulfilling specific roles, and utilizing tools. Key building blocks include providers, models, prompts, tools, and memory. This diagram illustrates the conceptual flow of an AI agent, from a user's input query to the final response, incorporating LLMs, tools, and memory for effective task accomplishment. The generative AI landscape has rapidly evolved since 2017's Attention is All You Need paper. ChatGPT's 2022 launch brought AI agents mainstream, with major providers like OpenAI, Anthropic, Google, and Meta now offering advanced models. When choosing a provider and model, hosted solutions are best for prototyping. Consider model size trade-offs for cost, speed, and accuracy. Longer context windows allow for more extensive context input, simplifying selection. Reasoning models perform internal logic to break down complex problems. They can take longer to process, but offer significant accuracy gains. Treat them as, quote, report generators, providing ample context and examples for high-quality responses. Crafting effective prompts is key. Explore zero-shot, single-shot, and few-shot techniques. Use system prompts to define an agent's tone and formatting tricks like capitalization or XML-like structures for precision, especially with advanced models. Structured few-shot prompting, using XML-like tags and multiple examples, allows precise control over agent behavior. This enables complex tasks, like entity extraction with specific output formats, making agents highly reliable. Agent autonomy exists on a spectrum, from low-level binary choices to high-level planning and task division. This course focuses on building low to medium autonomy agents, which incorporate memory and tool calling capabilities. This diagram illustrates the conceptual agent autonomy spectrum, showing how low autonomy, decision trees, evolves into medium autonomy, tool use, memory, retry logic, and further into high autonomy, task decomposition, complex planning, self-correction. Model routing allows seamless switching between different LLM providers for quick experimentation. Structured output ensures LLMs return data in formats like JSON, useful for tasks such as extracting job details from a resume. This conceptual diagram demonstrates how model routing works. A developer configures an LLM, and the router directs requests to the appropriate provider, such as OpenAI, Anthropic, or Google, based on the configuration. Tools are functions that extend an agent's capabilities. Designing effective tools requires detailed descriptions, specific schemas for predictable behavior, and semantic naming. Think like a human analyst when delegating tasks. This example shows a simple calculator tool with its Python implementation and corresponding schema for LLMs. Clear definitions ensure the LLM can correctly invoke the tool, making effective tool calling reliant on robust schemas. This diagram illustrates the conceptual flow of tool calling. A user query triggers the AI agent to analyze and call a tool, like a calculator, execute it, and then synthesize the result into a final response for the user. This diagram illustrates conceptual hierarchical memory. User queries feed into current conversation context, which adds to short-term memory. A memory retriever accesses long-term memory to combine recent and long-term context for the LLM to generate responses. Agent memory is crucial for maintaining contextual conversations. Working memory stores persistent user characteristics, while hierarchical memory combines recent messages with long-term memories. Memory processors like token limiter and tool call filter prevent context window overflow. This pseudocode demonstrates token limiter logic, which ensures conversation history stays within token limits by iteratively removing older messages while prioritizing system messages. This prevents context window overflow and maintains agent performance. Dynamic agents adapt their behavior at runtime. Guardrails sanitize inputs and outputs to protect against prompt injection and PII requests. Agent middleware handles authorization, ensuring accurate permissioning and security. This example shows a simple PII guardrail using Python-like pseudocode. It uses regular expressions to detect common PII patterns like email or phone numbers, blocking or sanitizing the input to prevent sensitive information leakage. This diagram illustrates the conceptual guardrail flow, where user input passes through a guardrail before reaching the AI agent and LLM. Similarly, the LLM's output also goes through a guardrail before being presented to the user. Agents' power is enhanced by tools. Web scraping and computer use tools enable browser automation and data extraction. Third-party integrations connect agents to user data systems like email, calendars, and specialized platforms, often via agentic IPaaS solutions. This diagram illustrates conceptual tool categories, showing how agents use various tools to extend their capabilities. These tools enable complex interactions and data processing beyond the LLM's inherent functions. Model Context Protocol, or MCP, is an open standard akin to a USB-C port for AI applications, proposed by Anthropic and supported by OpenAI and Google Gemini. It unifies fragmented tool definition and calling across AI providers, enabling standardized remote code execution. This conceptual diagram depicts MCP interaction, showing how clients, models, or agents query MCP servers for tool definitions, request tool execution, and receive responses, enabling seamless communication within the MCP ecosystem. Despite support from major players, the MCP ecosystem faces challenges. Fragmented registries create a discovery problem, lack of verification standards leads to quality assurance issues, and incomplete client implementations result in configuration complexity. Workflows provide structure for agents, decomposing complex decisions into smaller binary steps. They define branching logic, parallel execution, checkpoints, tracing, and chaining, enabling predictable outputs and robust observability. This diagram illustrates a conceptual workflow structure, showcasing how different steps are sequenced, branched, and merged to manage complex agent processes. It highlights the structured approach to agent execution and decision-making. Workflow primitives are fundamental building blocks. Chaining sequences steps for logical progression, branching triggers parallel executions, merging combines results from divergent paths, and conditions define execution paths based on intermediate results. This pseudocode illustrates chaining, branching, and merging. A query is classified, then summarized, and keywords are extracted in parallel. Results are merged, and a condition expands the summary if it's too short, demonstrating integrated workflow primitives. Workflows must manage external dependencies, often pausing for human input. Due to potentially long wait times, the workflow's state must be securely persisted. Specialized functions like suspend and resume enable seamless continuation of execution. This diagram illustrates the conceptual suspend/resume flow, where a workflow can pause, save its state, await external input, and then seamlessly resume execution from where it left off once the input is received. Streaming is crucial for a good user experience, making LLM applications feel responsive. What to stream includes LLM output tokens and workflow updates. Observability and tracing, using OpenTelemetry, provide insights into non-deterministic agent behaviors, showing step durations, inputs/outputs, and call metadata. This Python code snippet demonstrates LLM streaming using the OpenAI API. By setting !stream equals true tokens are delivered incrementally, providing real-time output and significantly enhancing the responsiveness of agent applications for a better user experience. This diagram illustrates the conceptual streaming flow, showing how LLM output tokens are continuously sent to the user as they are generated, rather than waiting for a complete response, ensuring a more dynamic and responsive user experience. In AI agents, non-determinism makes observability and tracing vital. Observability visualizes application traces, offering a clear picture of execution paths. Tracing provides granular telemetry, showing inputs and outputs of every function call in a nested tree of spans. OpenTelemetry is the industry standard for this, offering detailed durations, JSON inspection, and metadata for anomaly detection. This diagram provides a conceptual view of a trace, illustrating how OpenTelemetry captures and visualizes the nested function calls and their details, offering comprehensive insights into an agent's execution for effective monitoring and debugging. Thank you for watching Part 1 of the AI Agent Playbook from Prompting to Production. Watch rest in Part 2.